morning.
Good morning.
I have an announcement for coming a week because today is Thursday, tomorrow definitely is Friday, and on Monday I'm going to offer you again so-called in-class quiz for the material which we covered recently. It is including trigonometry, polar coordinates, and some problems about complex numbers. So we already handled that type of quiz. I will be going to offer you that coming on Monday quiz in the same manner as we already had recently. And this is my important announcement. At the same time, definitely, we are going to have some online quizzes, and we just have few topics which we have to cover in this class. We are quite soon we will be having a test for covered material, and we will be we will be working with another material about left limits, right limits, different type of asymptotes, graphs of complicated functions, and etc., which is also quite new material for you guys. Do you have any particular question in your mind which you like to address to me, or I can actually start solving more problems?
You can go ahead and start.
So I can start, right?
Yes.
Yes.
Okay. So we will continue our work with the same section. And this was section 9.6 from your textbook. So far, we talked about algebraic form, and I just a little bit gave you some feedback about another form, which is a trigonometric form, or we can say polar form. And as you remember, we, at the end of the lecture, we talked about powers of unit I, right?
Yeah.
Yes.
Okay. So what I'm going to do right now, before moving to another form, are you asking me something?
Oh, no, sorry.
Okay. Yeah, I say again, I can repeat that microphones are quite sensitive, and when you talk to someone in your room, we all can hear that. So I'm going to remove that paper. Do you let me do that?
Yes, that's fine.
Yeah.
Okay. What I'm going to do. So far, we talked about forms in which these numbers can come. I would like to show you some symbols for that particular forms, and solve some examples which can demonstrate what can be done with that numbers. Because if there are numbers, we need to be able to add them, to subtract them, to multiply, to divide, to raise to the certain powers, to take roots, and etc. Because they should be operational. So right now, I am going back to algebraic form, or another name is rectangular form. And this is how it looks. And I like to show you existing symbols. And these symbols are international. I did not create them. You can see capital R, small case E, re of z, im of z. What is the meaning of that? These are symbols for real part of z, and the real part of z is x. And imaginary part, we do not write yi, we just write down y. This is a coefficient for imaginary part. So if you see these kind of symbols in any math textbook, they have this meaning. They are talking about the complex number in algebraic form, where the real part is x, imaginary part has coefficient y. Is it clear?
Yes.
Yes.
Excellent. But now, I would like to ask you one question, and please think how to answer, and I will attend it while you actually work with that. Let's say I'm talking about real numbers right now. Which number is greater, 10 or 15?
15.
15, I'm boxing, 15 is greater. Which number is greater, negative 10 or negative 15?
Negative 10.
10.
Again, one more time, which number out of these two is greater, negative 10 or negative 15?
Negative 10.
Negative 10.
Negative 10. And can you give me simple explanation why you choose in first case positive 15? And in other case, you used negative 10. Do you need my help?
Yes.
Yes.
Why did I agree with positive 15 being greater number comparable with 10? Because actually is it located on greater distance from 0 on the right side?
Yes.
Yeah.
Does it mean that on the right side in the set of positive numbers, it is on greater distance from 0?
Yes.
Can we say it is on the more right side comparable with 10 on that
Yeah.
line?
Yeah.
Excellent. Why did we choose negative 10? Is it
This is closer to 0.
all negative numbers? Yes?
Yes.
Is it closer to 0 than negative 15?
Yes.
Can I say that it is on more right side from negative 15?
Yes.
So which means anytime when the number on the number line is on more right side, it is a greater number. Can we say so?
Yeah.
Mm-hmm.
Is it going to work for both a set of negative numbers and the set of positive numbers? English has again two magic words, yes or no. Can we
Yes.
say that for all numbers actually on the number line, that one will be greater, which will be on the more right side than the other one?
Yes.
This is
Yes.
what I was talking about. Now, can you please compare these two numbers? Negative 2 plus, let's say 3i, and positive 2 and negative 3i. One number and the other number. I even underlined them. Negative 2 plus 3i, positive 2 minus 3i. I'm asking the same question. Which number is greater than the other one? Please think how to answer, and I'm going to check your names. Okay? Simple question. So, today is April 30th. It is already last day of April, and I'm reading your names. Andrew,
Here.
Tima, I saw her. name. But now I do not see her. I do not see her name here in the list of students, unfortunately. Okay. Lorraine,
Here.
Lynn,
Here.
Juanita,
Here.
Yuran,
Here.
Gabriel,
Here.
Divina,
Here.
Chantal,
Here.
here. Who is next? Gongsi,
Here.
Kyle,
Here.
Matthew,
Here.
Julian, Nathan,
Here.
Alejandro.
Here.
Excellent. I'm done with that. And now back to my question. Which number is greater, -2 plus 3i or 2 minus 3i? Do we have any brave person who can start? Kyle, please, what do you think about this comparison? Which one is greater?
I don't know.
What were the numbers?
I'm comparing -2 plus 3i with +2 minus 3i and try to compare them from that point of view. Which one is greater? Andrew, what about you? Guys, why are you so silent? You scare me.
I think it's 2 minus 3i.
2 minus 3i is greater, in your opinion, right?
I think, yeah.
Okay, okay. What about Lorraine? Lorraine, what do you think about that?
I was gonna say the same thing actually, yeah. So 2 minus 3i.
Okay, Chantal?
I was thinking the same thing.
Okay. Can you ask me the same question, please, guys? Who is going to ask me?
Which of
Which
these
do
two
you
are
think?
greater?
You know what? I cannot answer. I do not know. I do not know which number is greater than the other one because we do not have that kind of, you know what, answer how to compare them. Yeah, I can compare real numbers because it will be normal. We establish certain criteria to answer that question. But in the set of complex numbers, or if we deal with imaginary numbers, nobody so far can answer that question. So my question to all of you was very tricky. I played really bad game asking you to compare them because we can have only one type of comparison if they are equal to each other or not. And this is the only one thing, what can I say? They are not equal to each other. Because if two complex numbers are equal to each other, they should have matching real parts and matching imaginary parts. And in nowadays, on our society, any extremely experienced mathematician so far cannot answer that question. I really apologize that I played that game. Okay? Guys, do you accept my apology, please?
Yeah.
Right.
But now at least you know that someone is quite annoying you. It can happen even during some kind of gatherings. It is not definitely during that quarantine time, but we hope it will not last forever. Because sometimes people like to annoy and they say, oh, okay, and you know what, they like to be asked certain tricky questions. You can ask them this question and you will be released to the end of that event. Only at the end of the event, explain them that this question was very tricky. So anyway, how to add numbers. And you know what? Some operations are good for certain form of the trigonometric, a certain form of, excuse me, complex number. Because if I need to add numbers or I need to subtract numbers, or even compare if they are equal to each other or not, because visually they can look different, but we need to simplify to come to that conclusion. The best form is algebraic. Algebraic form is the easiest form to perform addition or subtraction. Let's show how. Let's say we have two numbers, Z1, which is, let's say, 5 plus 9i, and Z2, which is negative 11 minus 2i. And I'm going to work with these numbers. Let me box these numbers so it will be more visual. And I'm going right now to show basic operations with that numbers. If you need to add them, it is very easy because you are adding separately real parts and separately you are adding imaginary parts. You can write this I in front of parentheses or behind, it is up to you, and proceed to the answer. 5 minus 11 is negative 6. 9 minus 2 is positive 7. So voila, this is your answer. Negative 6 plus 7i. Very easy operation to perform. Do you agree with me?
Yes.
That this is very easy way to add?
Yeah.
Thank you. Let's say we are subtracting Z1 minus Z2. Same approach. Real part minus real part, imaginary part minus imaginary part. So it will be 5 minus negative 11, which will be 5 plus 11, plus 9 minus negative 2, which is 9 plus 2. Don't forget about I. Which is 5 plus 11, 16. 9 plus 2 is 11. And you have your answer. This is your answer. So far, so good?
Yes.
Yes.
So, multiplication, Z1 times Z2. It is not the most preferable operation for that form, actually. But we can do that. If we just need to multiply two complex numbers, it will be not really heartbreaking operation. It will be not extremely tough. You will be just can use FOIL method, or you can use each by each multiplication, multiplying two binomials. So let me write it down side by side. Why I'm talking about binomials? Because in each of parentheses you have two termed piece, and multiply. So 5 times negative 11, negative 55. 5 times negative 2i minus 10i. 9 times negative 11, negative 99 I. 9I times negative 2I, it is negative 18I squared. Do you agree?
Yes.
Do we have like terms?
Yes.
Yes.
Let me underline these like terms right here in the middle. Are they like terms?
Mm-hmm.
Yes.
What about negative 55 and negative 18I squared? Are they like terms?
Yes.
I agree with you. Visually, they do not look the same, but I squared here, just that piece, I squared, is it negative 1?
Yes.
Look, I wrote it right on the top of I squared. I wrote equals to negative 1. So in this case, is it actually negative 18 times negative 1, which will be positive 18?
Yes.
So
Yeah.
which means, yeah, they are also like terms. And look what I did. I used that, I underlined using that waves. So, which means it will be negative 55, and I need to add that negative 18I squared, which is positive 18. And I am adding together negative 10 and negative 99. Don't forget to write outside of parentheses that I, and proceed to the answer. If you add negative 55 and 18, what do you get? Guys, please help me with calculations. Don't touch calculators. Do
37.
that mentally. Excuse me?
Negative 37.
Accepted, negative 37. If you need to add negative 10 and negative 99, what do you get?
Negative 109.
Yeah, I could not hear clearly. With
Negative 109.
109. Is it your answer?
Yes.
Is it just one person's opinion?
Yes.
Yes, okay. Box it. You can see it took a little bit longer time if we compare this with the time which we need to use to multiply just, let's say, real numbers. But if now I show you division, you will agree with me that division in algebraic form is really quite complicated. So what I'm doing, I'm dividing Z1 by Z2. Here we have the same rule. We cannot divide by 0 because 0 can be treated like another complex number for which real part is 0 and imaginary part is also 0 times I. So this is the case. We cannot divide by 0, not only in the set of real numbers, but in the complex set as well. So what I'm going to do, I'm going to write this like I wrote Z1 over Z2, and I will write down these numbers, 5 plus 9I divided by negative 11 minus 2I. Now question is, how can I divide complex numbers? The rule here is absolutely different, not that one which we use to divide real numbers at all. Have you ever heard in algebra, and you should learn this in Algebra 120, such kind of items like conjugates? Please quickly try to recall what you learned and tell me about that. I'm talking about conjugates. Which expressions give me that example. We have so many conjugates in algebra, in regular algebra. I'm not right now talking about complex numbers, which we call conjugates.
Aren't they the one where one expression is positive while the other expression is negative?
You are quite close. No, the explanation is not correct, but you have some smooth, you know what, but correct ideas. Okay, guys, do you need my help?
Yes,
Yeah.
please.
For the expressions of the second degree, conjugates are a plus b and a minus b. They are conjugate to each other. Why? Or because when you multiply these by each other, a plus b times a minus b, it will be equal to a squared minus b squared. Is it correct?
Yes.
Yeah.
But if we start talking about third degree expressions, it will be more complicated because we need to get, as a product, we need to get or a cubed plus b cubed or a cubed minus b cubed. And in this case, if we have a sum, so a cubed plus b cubed equals to a plus b times a squared minus ab plus b squared. So for, in this case, for a plus b, conjugate will be a squared minus ab plus b squared. And for a squared minus ab plus b squared, conjugate will be a plus b. It is quite complicated, but it is true. But for the second degree, they are easy. A plus b and a minus b are conjugates to each other. So in this way, if you have an expression which matches a squared minus b squared, you can easily factor it. You can factor it because a squared minus b squared equals a plus b times a minus b. What about complex numbers? In complex numbers, we also have conjugates, but we call them complex conjugates. And complex conjugates are a plus bi and a minus bi. They are conjugates to each other. I'm boxing these two numbers. These are complex conjugates. A plus b is a conjugate to a minus bi. A minus bi is a conjugate for a plus bi. They are complex conjugates to each other. Let's see what their product gives us. It is very interesting because you know what? We can use this in many problems. A plus bi times a minus bi. Can I use the formula from algebra, which we call difference of two squares? Definitely we can. There is no way, yeah, definitely you can do that. I mean, foiling and using that long way, but it is not an elegant way to solve these problems. It is much easier to use that formula from algebra, which we call formula for the difference of two squares. So it will be square of the first number minus the square of the second number. But for the second number, we have bi, and I wrote it down. So far, so good?
Yes.
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 Do you let me continue?
Yeah.
Equals a squared minus b squared I squared. Agree?
Yes.
Guys, power to the product. So I need to raise each component, each factor. So it will be b squared, I squared. You are not okaying that? Guys,
That's
Oh,
good.
we can't see.
you cannot see?
There we- Okay. Yeah.
Yeah.
I squared, is it -1?
Yeah.
Yes.
Mm-hmm.
Is it finally a squared plus b squared?
Mm-hmm.
Yes.
Look what we are getting. When we multiply complex conjugates, we are getting a squared plus b squared. And practically, doing this, showing this in the process, I actually proved that a squared plus b squared also can be factored. Only this time factoring a squared plus b squared, because remember, in the set of real numbers, a squared plus b squared was a prime. In the set of real numbers, you cannot factor it. But in the set of complex numbers, you can factor it. It will be a plus bi times a minus bi. So, and I'm going to box this as well. It is factorable, but it is factorable in the set of complex numbers. So far, so good.
Yes.
Yes.
And I started talking about complex conjugates, not just because I wanted to talk about these numbers. It is a necessity for us if we divide complex numbers in algebraic form. Because look what I'm going to do. I am going to look at the denominator. At the denominator so far only. What do we have in denominator? Is it negative 11 minus 2i?
Yes.
What is the complex conjugate for the denominator? Is it negative 11 plus 2i?
Yes.
Yeah.
Because if I had minus 11 minus 2i, its conjugate, complex conjugate will be negative 11 plus 2i. And please multiply top and the bottom by this complex conjugate. Do you remember we were doing that strategy, using that strategy when we were trying to get rid of irrational numbers in denominators?
Yeah.
Yes.
It is very similar, but this time you are multiplying top and bottom by the conjugate for the denominator. And proceed. Because the bottom part represents two conjugates multiplied by each other, I can apply that formula. Because A is negative 11, B is 2, this y, the bottom part, using shortcut, which is very elegant to do that here, plus 2 squared. Because again, for these conjugates, A is negative 11, B is 2, where A is the real part, B is the imaginary part. Or if you like, X is negative 11, Y is 2, and it is X squared plus Y squared. On the top, I need to multiply like I would multiply two binomials. So 5 times negative 11 is negative 55. 5 times 2i, it is plus 10i. 9 times negative 11, negative 99. And 9 times positive 2i, it is plus 18i squared. Do we have like terms on the top of that fraction?
Yes.
Can we
Oh,
see,
wait, yeah.
can we raise bottom numbers to the second power and add them?
Mm-hmm.
Let's do that. I will probably start with the bottom first. Negative 11 squared, is it positive 121?
Yes.
Yeah.
2 squared, is it 4?
Mm-hmm.
So I wrote them down. negative 55. Should I combine that with negative 18?
Yes.
Thank you. Is it going to be a real part? Yes.
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 Plus, should I add 10 and negative 99?
Yes.
And in outside of parentheses, should I write that I?
Yes.
Right. This is what I am getting. Can I continue?
Yes.
121 plus 4. Is it 125?
Yeah.
Negative 55 minus 18. They are both negative. What would be the result?
Negative 73.
Accepted. 10 minus 99. What would be the result?
Negative
Negative 88.
89.
Negative 89.
99.
Accepted. Should I write negative 89i?
Yes.
You know what? I was a little bit badly, I would not say shocked, but surprised for sure, when I saw that y Laplace is slightly violating the international traditions, because I cannot keep this as a final answer, but they keep these kind of expressions like final answers. This is a violation. We need to bring this to acceptable form of the answer, and this is an international rule, not mine just rule. It works even here in the United States. I worked with many publishers and textbooks, and I saw that actually answers according to international standards. We need to separate real parts from the imaginary part, because the official form of the complex number is z equals, I'm talking about algebraic form, z equals to real part plus imaginary part. This is why I'm going to follow this international rule. So it will be negative 73 over 125 minus 89 over 125, up to you to write I behind that fraction, or you can write this in front of the fraction. Honestly, I like to write them behind that fraction because it is like a coefficient of I, but if you place that in front of second fraction, I will not fight with you, I promise. This is how I wrote my answer. Can you see?
Yeah.
And I'm just following the international standard, because now it looks as real part plus imaginary part, because it is again the answer in the algebraic form of the complex number. If you can reduce these numbers, go ahead and do that. If you cannot, just leave this alone. Can we reduce 73 with 125? Guys, no, we
I
cannot.
don't think it can.
And we cannot reduce 89 with 125 as well. So we just leave this as they are, and these are our answers. Is it clear?
Yes.
Yeah.
So I do not have time today to talk a lot about operations with trigonometric form. I will tomorrow. But trust me, if I need to add or I need to subtract numbers, I would never choose trigonometric form. I definitely will be doing that preferably in algebraic form. But if I need to multiply, or I need to divide, or I need to raise to the certain power, definitely trigonometric form will be very attractive. Or if I need to take, let's say, root. Oh my God, because even square root of complex number in the algebraic form looks like a nightmare. This is why I would never, in my goodwill, I know the formula, but I would never use by my will, by my choice, let's say, algebraic form to find square root. I'm not even talking about cube root, fourth root, but if you have a trigonometric form, you can find any root, even let's say 99th root or 1341st root of certain number, because it will be definitely, it will take some time. If your index of the root is really high number, it will be just a little bit more time, because according to all this theoretical information, if we have any number, it can be written in the complex form. And if I need to find the cube root, let's say, of 8, and if in the set of real numbers, the answer was like just 2, not anymore in the complex set, because according to that rules in the complex set, if you have a cube root of 8, it should have 3 different answers. And one of that answers, yes, it will be 2, but 2 others will be other numbers which are not from set R. And I will definitely show it to you. I would like to continue with another form, which is the last form which we have in the set of complex numbers. And this is so-called exponential form. Do you let me do that? Can I start talking about that form?
Yes,
Yeah.
please.
On page number 388, right in the middle of the page, you have a box. You have a box, and this box is very well known in math world, like Euler's formula. Euler is a very genius, I would say, mathematician, European, and he actually worked not only in his native country, because he was so smart and so multi-talented that all countries, and it was in, I think, 18th century, they tried to get him trying to attract him with huge salaries and etc. That they were inviting him to establish university academies, to establish math education in their countries. And this is well-known formula, which is Euler's formula. This has quite complicated proof. This is why I'm going just to write that formula. EI to the theta equals cosine theta plus I sine theta. This is your Euler's formula. Very well known in math and being used a lot. This is again Euler's formula. And look what we can do in this case. And now I definitely will show you the very tight connection between trigonometric form and exponential form of the complex number. Look what we had for the trigonometric form. It is, I lost that piece of paper from, oh, no, I found that. This is that formula number 2, which we had on the previous day. So Z equals, I'm just copying this formula right here because I don't want to grab that paper constantly. So it was R cosine theta plus I sine theta. This was, again, I'm going to write down the same number too, because this was named best by us like formula number 2. Can you see? Did you find this in your notes from yesterday?
Yes.
Excellent. And let's see what is going on. I'm going to work a little bit with this trigonometric form. I'm going to copy that R. What about this parenthesis which I have in this formula? Is it actually e to the I theta?
Yes.
Yeah. So which means I can write the new form for that complex number. Do you understand where it is coming from?
Mm-hmm.
And voila, this is your exponential form. This is formula number 3. This is the third form. You can write this in that form, or if you like, you can write this in that form. I'm writing. Your book has that one, which I wrote at the beginning, but you can write theta times I. Up to you. For people who like to place theta in front of I, this will be like 3 with this star, but it is same thing. Or. So this is your case. When you have the third form of trigonometric, from trigonometric form, you got the third form, which is so-called exponential form. And you probably understand why it is called exponential form, because you have theta I and the exponent for base e. Can you see that?
Yeah.
Yes.
And now, guys, basically, I told you about many things already. Definitely, I will be proving tomorrow extremely beautiful formula, so-called the Morse formula. It is on page 391 in your textbook, and you will discover amazing things actually about this formula. Anyway, I prefer right now to go to page 392, where I have different problems, and I can solve these problems. Is it okay? Because I already showed you how to add, subtract, but I will grab right now one of problems from 1 through 6 to show how to work with these numbers. These are problems from 1 through 6, and we need to express the complex number in polar form. But I don't know why they call this just only polar form, because polar forms here are 2 forms, number 2 and number 3, but they have the form which is an exponential form. Are you okay?
Yes.
Let's say I'm working with problem number 6. Problem number 6, z equals -1 plus 3i. This is problem number 6.
We can't see it. Okay.
Can you see now?
Yeah.
Yeah, it's fine now.
Okay. What kind of form should we get? We need to get that in the following form: r, e, theta, I. So this is our form for the answer. So which means I need to find r and I need to find theta. Okay, let's do that. First, I will start with r. A real part of the number is -1. Imaginary part, y, has value of 3. Do you agree with me?
Yeah.
So R equals square root x squared plus y squared, which is -1 squared, which is 1, 3 squared, which is 9. So we have R equal to square root of 10, and I'm done with R. Now, I will continue. Now I need to find that theta. Tangent of that theta equals y over x, which is here 3 over -1, which is -3. But tangent is negative in the first quadrant and in the third quadrant. In the first quadrant, in the third quadrant, positive. In the second and fourth, negative. So which means we need to choose one of quadrants having second and the fourth. But look what you have. Real part, and I long time ago showed you that number in the XY coordinate system. Real parts all the time are on the horizontal axis. Imaginary are on like so-called y-axis, it is vertical. So, excellent. In which quadrant you have that number if your x is negative and y is positive?
Second.
Accepted, definitely it is a second quadrant. So practically, I need to solve that equation to find that angle for which tangent is equal to -3 and theta belongs to the second quadrant. Excellent. So look what I'm going to do. I will sketch that small circle, or it looks horrible in my interpretation. Second quadrant angle, like something right here. And look what I'm writing down. That theta equals, can I say that it is equal to pi minus that small angle right here? Can I?
Yeah.
Yeah.
But what about that small angle? This is the reference angle, and this is actually arctangent of -3. Pi minus arctangent of -3. And you can plug this in your calculators, please. Just entire thing. So turn on second button, that corner, which releases pi, minus, I need to check the mode. Mine is in radians, so I'm satisfied. So minus, again, second button, tangent button, and negative on the bottom of the calculator. So -3 and close parenthesis. Oops. Can you see anything, guys?
Yes.
Yeah.
I'm sitting next to that window. The light is quite bright. And push enter. Pi minus arctangent of -3. Or I said -3, I really apologize, because we subtracted, well, erase that. I really apologize, I made a mistake accidentally. Pi, please do that pi again. +3, because we are talking about reference angle. Switch that minus to plus and re-enter. So it will be second. Pi, I really apologize. You have the worst professor. So arctangent of +3. So, and all together, I am approximating to the nearest 100. Or let's do that to the nearest 1,000. 1.893. That's it. Now I'm ready to write down my answer for that z in the new form. So it will be z approximately square root of 10 times e to the 1.893i, and this is my answer. But knowing that r and knowing that theta, if you need another form, let's say trigonometric, you all the time can do that because you found that theta and you found that r. So it is up to you. They are not asking us about that, but if you like to write this in the other form, so it will be cosine of 1.893 plus I sine 1.8993. And this is a trigonometric form, which is another polar form also for that angle. So let's do that. I will be calling that the last one trigonometric form, and if they like to use in the book polar form for exponential form, I will be using polar form for exponential because I don't want to confuse anyone. I am done for today, and I will be releasing many interesting facts tomorrow about these problems and forms. Did you have an opportunity to have good notes?
Yes.
And again, I will try my best uploading a video on YouTube, so you will have another opportunity to go over the same lecture again if you need that. Can I release you guys?
Yeah.
Yeah.
Again, stay safe and well. I wish everyone and your families good, actually, health. It is very important for us. And everyone, please don't forget about your math assignments and other assignments. Stay well and healthy, and I will see you tomorrow. Everyone, have a nice, beautiful day.
Thank you.
Goodbye.
Have a nice day.
Goodbye, ladies and gentlemen.